Now, this is an equation, E equal mc squared, a very famous equation, and for good reason. So here you will recognize these mushrooms. So these are photos of the atomic bombs which exploded in Hiroshima and Nagasaki at the end of Second World War. And here you have a picture of stars. So what atomic bombs and stars have in common? Well, they are both fueled by the effect of this equation. There are nuclear reactions in which mass can be converted into energy, namely nuclear reactions in which the final mass is smaller than the initial mass, and the difference in mass multiplied by c squared is released as energy. This can happen through nuclear fission, in which a large nucleus divides into other smaller nucleus, or nuclear fusion, in which smaller nuclei form a larger nucleus. But in both cases, the final mass of all the reaction products is smaller than the initial mass. And by not much. For example, for fission, here you have at the beginning you can have 236 units of mass, which is a proton mass, and at the end you have 235.80. I mean 0.2 of a proton mass. This is a small mass difference, but of course there are many, many nuclei that are in a particular reaction. Now, fission is what is at play in atomic bombs, in the energy released by atomic bombs, A bombs, and in all functioning at present nuclear power plants or nuclear reactors use fission. Fusion is at the basis of the energy released by all stars, including our sun. So we owe our life on Earth to nuclear fusion. It is also what is used in H bombs or hydrogen bombs. And it is what is used in controlled fusion or hydrogen reactors. At this point, hydrogen reactors consume more energy than they produce. But if this balance could be reversed, I mean, if they could be made to produce more energy than they consume, then they would provide clean nuclear energy. And many people are working in this idea, in this possibility. So you see that the importance that it has for our everyday life, special relativity.